Okay, so today is free radical reaction day. These mechanisms are super different from everything we've always done. And the reason I saved them for the very end is because they are also super rare. And this reaction that we're kind of covering today, where you turn an alkane into an alkyl halide, I don't even want you to put it into your functional group interconversion flowchart. It's a mess of a reaction. It's not great. It can work under really weird circumstances, but the main reason we're doing polymers and talking about free radical reactions today is so that on Monday we can talk about polymers, because polymers matter a lot. Free radical mechanisms don't really have a lot of place in synthetic organic chemistry. They don't really have any good place in biological chemistry. In fact, you guys have probably heard about free radicals before and free radical scavengers, but mostly in the context of these are bad things for you, right? So when you hear people talk about studies with chocolate and red wine being good antioxidants, so they help you get rid of these toxic free radicals, what they're talking about is actually these unpaired electrons. So free radicals are super dangerous in your body because, as we see here, and we've seen in these propagation steps, a free radical, so an unpaired electron, really wants to have another electron. And most of the electrons in your body exist in pairs. And so in order for that one electron to pair up, it needs to take apart a bond or a lone pair where there's two electrons already, which was stable and good. And to do so, it has to take one electron out of that pair and it leaves one electron behind. So an odd number, no matter how you do addition or subtraction, is always going to leave you an odd, and an even is always going to give you an odd. And so you always end up with one kind of left out. And then what do they want to do? Well, they want to rip apart a stable, happy bond or pair so that they can become stable, but it makes a new one. And so this idea of a propagation is like it's not a big deal for doing it in a flask. You keep turning a radical and a bond into a new bond and a new radical. And then that new radical breaks up a bond and makes a new radical and a new bond. And then that radical breaks up a bond and makes a new radical and a bond. And it just keeps going over and over and over again. And for the most part, we never really get rid of those radicals. In a pot that's a little round bottom flask, it's not a big deal. In our bodies, it is a big deal, because if you start ripping apart bonds indiscriminately and making more radicals that can rip more bonds apart indiscriminately, it really usually leads to bad things. Notably, your DNA has a bunch of double bonds. And when we start to mess with that, we start to mess with replication. And that's often what leads to cancer. So this is why radicals are pretty bad. And we try to eat foods that kind of get rid of them. Mostly what they do to get rid of them, because you can't get rid of an unpaired electron really, unless you give it another unpaired electron, but the chances of them finding each other are super slim. And so biologically, mostly what we try to do is stabilize them so that we can then excrete them before they cause too much damage. But free radicals are something that you'll hear about in medical science. And people will talk about them kind of in terms of, you should eat this or drink this because it gets rid of free radicals. And to a certain extent, some of that is true. You don't really need wine to do it. You can just eat grapes because it's mostly in their skin. Blueberries are great for that, for antioxidants, but there's a lot of foods that have antioxidants in it. And so it's just something to be aware of. But when you hear about free radicals in real life, this is where it means the same thing. It's an unpaired electron, which do a lot of these same reactions, but just keep in note that it's this propagation where the main thing they do is break up bonds, make new radicals, break new bonds and make new radicals, and keep making more radicals. All right, so we're going to go through this, but I want you to focus mainly on the propagation. The initiations are pretty simple. I gave you 4 different versions of initiators in the video. You don't need to know the structure of AIBN. You do not need to know the structure of NBS, but you need to know that those things, you don't even need to know what those necessarily stand for. Those are free radical initiators. Basically, they serve to make radicals. And once you have a radical, radicals will start doing that propagation stuff. So the ones I put on here are pretty simple, but these are going to be the ones that we're mostly going to focus on, at least for the halogenation reaction we're doing right now. So hello,
Sorry, I'm late. I think
You're
I
here.
pulled something on my back, so I'm really sorry.
I'm glad you made it. All right, so this light plus chlorine is going to break it up. And what happens is that this bond gets split. And so another new thing today, in addition to these weird mechanisms, is that we should be drawing our arrows with only half of a head. So this is how we've been drawing arrows forever, like that. And what this means, what we've decided that this means, is that a full-headed arrow means that you've got two electrons moving together. And that's how we've done 100% of our mechanisms for all of this class. When you're moving, so this is like when you're sharing a lone pair or you have a bond. When you only have one, what we do is a little half-headed arrow. So it kind of looks like a fish hook. Some people like to fill in their arrows. And so that would be kind of half filled in. But what that is telling you is that only one electron is moving. It's half of a pair, so half of a head on your arrow, as opposed to two electrons moving together. So this is what we've been doing forever. And this is still going to be the most common thing. But for this outcome, when we're looking at free radicals, you're going to have one electron moving at a time, and those one electrons moving at a time should technically only have a half of an arrow. Please try to do that. I'm not going to count it wrong if you draw the wrong type of arrow, but you've got it drawing in the right place, but please try to keep track of that. There's a lot of weird new things to keep track of in this outcome. All right, so when you add light to chlorine, chlorine pulls really hard on electrons, and both of those chlorines are pulling really hard on electrons. And so this is a really unstable bond. Think of a chlorine as a leaving group, and so its neighbor is an electrophile. Well, simultaneously, this chlorine's a leaving group, and so that chlorine's an electrophile. So Cl2 is really like two really, really equally strong kids playing tug of war. No one's gonna win, but they're just gonna keep yanking on those electrons and fighting over them all day long. So kind of the only way that this can end is if you actually split that bond in half. So think about like just cutting that rope in half. Everybody gets half a rope, right? No one's really happy, but that's the way that that's the only real way to satisfy this. And so that's what light does. So H nu is how you abbreviate photons, which is the smallest packet of light. So in a similar to way that when we put in a delta, that means heat. H nu means light. And so what light will do is it breaks that bond apart. And the way that we draw this is we draw arrows starting at electrons. Remember, arrows always start at electrons. We're never showing the movement of a hydrogen or a chlorine. We're showing the movement of electrons with mechanisms. So we take those two electrons and one goes this way with a half-headed arrow. And the other one goes that way. Both arrows should start at the bond because there's two electrons in a bond. You split one to the right and one to the left. And that's how they break up. And when we do that, the product of that should be that each of those chlorines is going to exist with now a free radical. In a lovely ideal world, free radicals will bump into each other, but life's not that nice. So just imagine that this never happens. There is a reaction called termination that we think about sometimes where two radicals find each other, but I would just basically want you to assume that that'll never happen. And just making that assumption that that's really never going to happen is probably in the best interest of everyone, because propagation is going to happen a lot of times. Termination will sometimes happen once. So just imagine it would be nice and neat for these two little guys to find each other and pair up, but there was a reason that they split up in the first place. All right, so the same thing happens down here, and these are peroxides. So you guys probably have hydrogen peroxide in your house, or maybe your mom has hydrogen peroxide in your house, or your dad has, or wherever it's in probably in a bottle. Anybody have hydrogen peroxide in their house? Okay, what does the bottle look like? Brown, right. You know why it's brown? Yeah, it keeps the light out, because this is what light does to peroxides. Peroxides are two oxygens, which are really electronegative, pulling on the same pair of electrons. Again, it's kind of like these two really strong kids playing tug of war. And by themselves, they're pretty stable. But if any light gets to them, that same mechanism is going to occur where that bond will snap in half and both of those oxygens will get one electron. And so you would end up with two things that look like that. Two oxygens with a free radical, which can then go on and do reactions. And so peroxides and halogens with light are normally what causes our free radical reactions to begin. So also, just think of AI being, so again, I told you don't have to worry about it. It's going to make a radical. NBS is going to make a bromine radical, but these are all going to make radicals. That's as much as I need you guys to know for these guys. You're going to make a radical. Right? These are the ones to tease out in terms of mechanisms. Those are a lot more complicated, so I'm not going to sweat them for this. But these are your radical initiators. We need these if we're going to start a free radical reaction. That's what initiation is, it's starting. All right, so that's not really the business end of this. This is kind of a precursor to radical reactions. So once you have a radical, then you start going through this mechanism. So this mechanism is weird. It's different from what we've done in the past, but here's what it is repetitive. It is always the same two steps. So once you know how to do these two steps, you're just going to be repeating it. There's not a whole lot to figure out. It's kind of something to just learn how this works. And once you learn how it works, it's just always going to go that way. So the propagation, whether we do it with this or on Monday, we're going to look at doing it with alkenes to make radicals. It's always going to be something like this. This is not arsenic or whatever, or boron or carbon. What happens is that you've got that unpaired electron, which needs a buddy. So the way that we draw this mechanism is it's going to pull an electron out of this bond. And so we imagine them making a bond to each other. But what we've done to make bonds in the past is have someone share a pair of electrons to make a new bond. But that's not what happens here. They kind of meet in the middle. So if Avery's got an unpaired electron, right? You're our home wrecker, you're going to rip someone's bond apart, all right? Then what you want to do is you want to contribute one, but you need someone else to bring one and kind of meet you in the middle. And so this is Avery. That worked out great. All right, so this is you. You are just going to share one electron, but you're not really sharing it with that boron. You're trying to make a new bond. I'm sorry, I just said that's not boron. Imaginary element B. You're sharing that one electron to make a new bond. And what you're going to do is you're going to take one electron out of this pair. You don't have to jam your electron in there to do that. You just need to convince one of those electrons to meet you somewhere in between. And so we take one electron out of that bond and one electron from this free radical. And what that's going to do is make a new bond between A and B. So whichever two species are making that new bond, you're going to have one of the electrons comes from a radical, the other one comes from a bond. But looking at this pre-existing bond, this stable, happy pair of electrons that existed before Avery came and tore it apart, you had two electrons there, right? So you ripped one of them out, and now there's one electron left behind. So where would the other electron go? Well, A and B are running off together. So who's left behind? C. And so the other electron is going to go to that C. So this is the abandoned partner. So whoever A is with the radical, it's going to break somebody off and make a new bond with them. So good news, A becomes stable because in the product of this, what we've done is A and B made a new bond and they are more stable, but in the same process, they ended up with someone else making a radical. This is what both steps of propagation will look like. It's that you start with a radical and a bond. You take half of the bond and the radical to make a new bond, but then you leave a radical behind. So how many arrows was that? 3. Because it's showing what happens to 3 different electrons. One that was a radical by itself and the 2 that were already in a bond. And you need 1 arrow for each of those bonds. So propagation must always have 3 arrows. Because the 3 electrons are kind of moving all separately in their own way. So a lot of these bridges were incorrect, and that is okay. I wanted you guys to practice this ahead of time. Just fix it and make sure that you're doing things correct. A lot of them were halfway right or mostly right or anything like that, and that's fine. Some of them were perfect. That's fine. It's not where you are right now, it's where you are next Wednesday, and that's why we're practicing this kind of thing together. All right, so looking at that and kind of comparing it to the situation we have right now, we're just saying we already made a chlorine radical. We made it by doing this kind of thing above, but we didn't need to do this a bunch of times. We really only needed to do it once. And then you got 2 chlorine radicals, and each one is going to keep propagating over and over and over again. So if you do this once, you can do propagation hundreds and hundreds of times. You don't need, I mean, technically infinite times. You don't need to keep making a radical. You only really need to do initiation once. That's why initiation is necessary, but not really a big part of this reaction. All right, so looking at what we've got here, we've got that chlorine radical, and this is definitely what's going to kick off our reaction. And then we've got a bunch of different things with bonds. We've got a chlorine bonded to chlorine. We've got carbon bound to carbon, and we've got carbon bound to hydrogen. So this is a random thing. Chlorine radicals are going to rip electrons off, break bonds kind of at random. They don't really care where you get the electron from. They just need one to become stable. So technically, this chlorine radical could rip apart a chlorine-chlorine bond, and probably does. But if it did that, it would make a new Cl2 and a new chlorine radical. So that's probably going to happen, but we wouldn't even know because the products are the same thing as the starting material. So this is a haphazard, random ripping apart of stuff. And it looks like we're only going to follow kind of one flow. But I just want you to be aware that other stuff happens, but mostly that other stuff doesn't get you anywhere. That's why we're not paying a lot of attention to it. So ripping apart this doesn't get you anywhere, which just really leaves us with ripping apart this alkane. All right, there are 7 different bonds in this ethane, but 6 of them are identical. They're just CHs. And the other one is a carbon-carbon bond. A carbon-carbon bond is buried in the middle of the molecule. And so carbon-carbon bonds do not get ripped apart, not because they couldn't, but just because they're relatively inaccessible compared to the CHs. The CHs are all around the outside. And that's just going to be the easiest thing for chlorine to break apart, and that's what it does. So you can pick any one of them. It doesn't really matter. But what we're going to do, all right, Avery, this is still you. You're coming in here with your electron, and what do you want? Just one electron. So what you need to do is break up one of these bonds. You don't have to go and do it. You just need to have your electron, trying to figure out the right word to say. It always seems like seduce is the right arrow, but that seems a little bit salacious. So you are just trying to attract another electron to you. Does that make sense? All right, so you're trying to pull one of those electrons and meet you somewhere. And so one of those electrons from a CH bond, and it doesn't matter which one, is going to kind of meet you halfway. And you're going to make a new bond with that hydrogen. Avery, is it okay if I pick on you all day for being the free radical? Okay. Well, it's good to remember things. All right, so this is what we're going to do. We're going to make a brand new bond between hydrogen and chlorine. I'm going to kind of veer that off. And we're going to make a new bond between hydrogen and chlorine. That's technically not really going to matter because, once again, it's still organic chemistry. So we're focusing on what happens to the carbon chains. All right, so I'm not done with my story. What am I missing? Yang, what am I missing here? Okay, we do need to do that eventually, but just in terms of this first step, this story we're telling first, I've taken one of the electrons out of the CH bond. There's still one more left behind. Where does it go? So this bond was between carbon and hydrogen. One of the electrons in the bond ran away with hydrogen. Exactly, it would go back to the carbon. So the other electron would move over to the carbon. So what we have done up to this point in this class again is to, if we were breaking a bond, we would move both of these electrons that way, or we would move both of those electrons that way, because we always moved 2 electrons together. That doesn't happen for CHs, so I'm going to erase those. That's to try not to confuse you. But when we're moving electrons one at a time, we need to describe where all of the electrons that are moving go. And so if you've got a bond is 2 electrons, so you need to describe where each of the electrons go. So this is the arrow that usually gets omitted, and your mechanism is wrong if you omit that arrow. So you need to have 3 arrows in all of your propagation steps, right? So that's what's going to happen. And what that will mean is we make a new stable, happy bond between hydrogen and chlorine. Congratulations, chlorine, you found your partner. But now we have screwed over that carbon and it doesn't have a bond anymore. And so it's going to end up looking like this. It's going to have 1 radical. So that is our first of our 2 propagation steps, is a chlorine radical rips apart a CH bond, makes a new HCl and a new carbon radical. The second propagation step is going to mechanistically look exactly the same. It's some radical is going to tear apart a stable, happy bond and make something new. So let's do, so that's step number 1. This is step number 2. Again, these are propagation step 1 and 2. So it's not initiation. We're already past that. All right, so this is our radical. This is definitely what's going to do the ripping apart of bonds. And once again, this is kind of indiscriminate. So here's where our possibilities for bonds are. In this flask, we've got carbon-carbon or chlorine-chlorine, and we also have other alkanes. It is very much possible that this carbon radical could get together and break off a hydrogen from another ethane. But that would give you a new ethane and a new carbon radical, which would mean that the products of that reaction would be exactly the same as the starting materials. So that may happen, but you would never know, and it doesn't get you anywhere. Again, this is indiscriminate. It reacts with whatever, but reacting with this wouldn't give you anything new. So what's the other thing you could react with? ClCl, right. I said earlier, it's totally wishful thinking to say that a radical and a radical are going to find each other, right? There are no wonderful, beautiful endings in free radical. It's just a path of destruction, right? Look what you've done, free radical. You made more free radicals, which make more free radicals, and that's all that ends up happening. So I'm a pretty optimistic person, but free radical reactions, it's just sadness over and over and over again. All right, so here's your radical. What does the radical do? Meets halfway. So this chlorine carbon is going to share its electron, and who is it going to make a new bond with? Right, one of the electrons, so it will be with the chlorine. Exactly, but the mechanism is, again, showing the movement of electrons, that one of the electrons from that bond is going to go over and make a new bond with that carbon. Yay! But at the same time, what else happens? Yeah, the other electron from the bond goes to make another chlorine radical. And so we will have, after our second step, we now have a chlorine attached to that carbon, and we're making a brand new chlorine radical. And so we took a radical, broke up a stable, happy bond, made a new bond, yay, but then a new radical. And so this is now going to do the same thing as before. This is indiscriminately going to break a bond apart, and you don't know which one, but it's going to go through and break bonds and break bonds and break bonds. And this kind of thing happens over again, over and over again. You'll do step 1, step 2, step 1, step 2. And because the product of step 2 that's so reactive, which is the chlorine radical, is the starting material for step 1, then you don't need to keep making radicals through initiation. Propagation makes a carbon radical, and then it makes a new alkyl halide and a chlorine radical. Chlorine radical will make a new carbon radical, which then makes an alkyl halide and a chlorine radical. And it just goes over and over and over again. And technically this could go infinite. Yes, sir.
Could it not just keep like pulling off hydrogen off of that carbon?
Off of this one right here?
Yeah.
Yes. So the reason that it tends to react more with an alkane and less with an alkyl halide is that alkanes are pretty stable in terms of the fact that they have these neutral carbons and neutral hydrogens. All of those bonds are nonpolar. But when you start introducing alkyl halides, this molecule now has a partial positive here, right, at that chlorine. So this is kind of an electron deprived molecule. And so pulling a hydrogen off of it would be harder than just pulling a hydrogen off of that one. So if you're looking for electrons, this is kind of like a paradise of electrons, these alkanes are. All the electrons are shared evenly, and it's easier to rip them apart. The electrons in this molecule are being inductively pulled to that chlorine. So there's generally like a smaller amount of electron density. It's harder to pull apart. So what we see, it makes complete sense, but what we see is usually they'll end up reacting with the alkanes instead of the alkynes.
Did it have moved with any like specific bond of hydrogen or is that one?
This is a great question. So we're going to move on to the next question, and which provides an example of what you were just asking. But when we look at this molecule, all of these CHs are identical because they're all symmetrical. And so it wouldn't really matter on ethane because it's just two CH3s and they're all the same. Yeah, so this is perfectly even. And so you wouldn't, I mean, basically what you're making, if instead of drawing it that way, we drew it as a line angle structure, it's just two carbons with a radical. And which side has the radical doesn't really matter. They're exactly identical. So where it matters is in a question like this one. So here I drew a line angle structure. So you had to draw in your hydrogen if you wanted to draw this mechanism correctly. If you didn't draw your hydrogen, you wouldn't be able to draw the mechanism, right? Because what happens is you pull off the hydrogen. So when we draw those hydrogens though, this molecule is symmetrical around the center, but not all of the carbons are exactly the same. You think about NMR environments, these two would be the same environment, the CH2s in the middle, but the CH3s are different from the CH2s. It doesn't because they're all sp3s, they're all making 4 single bonds. Secondary and tertiary?
Yeah, that.
Yes, it has to do with secondary and tertiary. All right, so let's look at a radical. You're a carbon radical. What's your fundamental problem? Right, you got too few electrons. In fact, you don't have a full octet. You only have 7 electrons. So what would you like more of? Electrons. So what kind of neighbors make you more stable? Carbons, right? Because carbon neighbors share electrons. If you don't have enough electrons, then carbon neighbors make you more stable. So the rules for stability of carbon radicals are exactly the same as they are for carbocations, because carbocations have the exact same problem. They don't have a full octet, they're deprived of electron density, and so more carbon neighbors make them more stable. So this is not enough because it has 6 electrons. This is not enough because it has 7 electrons. But whether you're 6 or 7, it's less than 8. So they have the same issue. So where would it be more stable to have a carbon radical? On a primary carbon or a secondary carbon? Secondary, exactly. And so when bromine pulls this off, from the bromine's point of view, I would suppose it doesn't really care. It just wants to rip off a hydrogen. But as we've seen a lot of times, you tend to get the more stable product. And the more stable product of this reaction, at least intermediate, I guess, would be to have a radical on the secondary carbon. That being said, you will get a mixture. This is part of the reason that this reaction is the PITS, is you will get a mixture of a radical here and a radical there, but the most common one would be the most stable one, which would have the radical at the secondary carbon. So I asked you guys to do carbon number 2. If you did the end carbon, I mean, you can do the mechanism, but that's just not the most abundant or most stable product. So to draw out this reaction, you need to draw in your hydrogens because the CH bond is what we're ripping apart. So the story is going to look exactly the same. You've got a bromine radical, and that is your instigator of this issue. It's going to attract to one of the electrons in a CH bond. But again, note that the CH bonds of one of your secondary carbons would give you a more stable product. So these are the ones where you can pull electron out. So you're kind of meeting in between, and it doesn't really matter where. This is somewhere in between. You're going to take 1 electron out of that bond. And what am I missing? That third arrow, right? So you have 2 electrons in a CH bond. One of them runs away with hydrogen to start a new life with bromine, and the other one goes back to the carbon. So this is always going to be a pretty small arrow. Drawing these relatively big will help you to kind of see them and not end up jammed too tight. So if you're used to drawing things super tiny, maybe draw it a little bit bigger in this case, but most folks end up drawing these CH bonds really small, and sometimes it doesn't help. So when we do that, Again, these arrows start at the electrons, which are in the bonds. There are no arrows that start at H's or C's. They always start at the electrons. All right, so what this story is telling us is that this radical is getting together with one electron from this bond, that bromine and hydrogen are making a new bond, and they're gonna run off together into the sunset. Good for them. But what we have made is now a new carbon radical, specifically on one of those interior carbons, like carbon number 2. So you can draw out all your hydrogens. There's still one hydrogen left here. And there's hydrogens, the rest of these are all just filled in with hydrogens as they should be. But this makes a new radical at carbon number 2. And what could this radical react with? Right, so it could react with another alkane, which would give us nothing new. It could react with HBr, which would actually just go backwards. Or it could react with Br2, which would give us something new. Don't write Br2, draw out Br2, because you need to show the movement of electrons. All right, I wrote this red, so we'll put in some new colors here. All right, Gabe, tell me what this mechanism is going to look like here.
You're going to have the radical lead the electrons from the Br2, and one of the other electron on the Br2 will go to the Br, or the other.
Great, perfect. Do you see how repetitive this is? Practice it, and once it gets boring and you know that you're doing it correct, like check your answers, but once it's boring, you know that you know what you're doing, and it's always going to be the same every single time. The only thing that will be different about this reaction is kind of where it's happening, but where it's happening primarily is going to be just what gives you the more stable radical, which is tertiary is more stable than secondary, secondary is more stable than primary. Something with resonance would be more stable than something without resonance, blah, blah, blah. All that stuff that hopefully we know. So that would attach a new bromine to this carbon, and what would be my other product? And so this is propagation, basically propagation step 1 and propagation step 2. Well, you don't usually end up with hydrogen radicals. Hydrogen radicals are super unstable. We find that we don't usually end up making them. Halogen radicals are actually the most stable, kind of in these big halogens, kind of follow the trend of like negative charge is more stable, lower positive charge is more stable, a radical actually ends up being more stable than that. So hydrogen is actually our least stable radical. You never really see it being made throughout the course of these reactions, but it kind of doesn't really have much of a chance to. You could make the case that maybe this radical here would like to pull off bromine and make a hydrogen radical. But what that would mean is that of this pair of electrons, HBr, that you're giving the hydrogen the extra one, and bromine is always pulling harder. So if this bond got broken up by a carbon, you would make a new bond with hydrogen and give the bromine kind of that extra electron. So that would just go backwards. So we never actually see hydrogen radicals in spectrum. Good question. So here what I did is I drew step 1 of propagation, and then I used the products of that to then just move straight into step 2. That was the way I did it. Here I drew it out where I did step 1 and I just redrew the products and did step 2. These are 2 different ways to do the exact same thing. Choose whichever one you prefer. It's absolutely fine with me. Either way, you start with a halogen radical and an alkane. You make a new HCl and a new carbon radical. And that carbon radical causes you to break up a halogen, and it makes a new alkyl halide and a new halogen radical. Don't memorize those words, but just do this reaction and you'll see that it just gets really repetitive because it does the same thing over and over. How do you feel about this? Good? All right. Before we get down to this last one, which is more of a lead into next week, let's go ahead and, next week as in Monday. Let's go ahead and I'll have you guys do some more examples. All right, so let's start with this molecule right here. And we are going to use, all right, I'm going to tell you NBS. Anybody remember what NBS is? Okay, so NBS effectively reacts as if it's Br2 and a bromine radical. So it's N-bromosuccinimide, which, so this is, the reason that we have this is kind of an extended release bromine. So instead of tossing in Br2, we can toss in NBS. And as a result, it's this really nifty thing where every time you do propagation once, then NBS releases one more effective Br2, and then you'll do it again. And so what it means is you don't have a lot of Br2 hanging around. For this kind of reaction, it wouldn't really matter. It would matter a whole lot. I'll give you another example in a minute of when it would matter. But just think of it, it's just like what we were just using. It acts just like bromine radical and Br2. Bless you. So what you guys should be doing right now, step 1 and step 2 of propagation. So draw those arrows. And to draw the arrows, you're gonna need to draw your hydrogens. At least one of them. Great. Looks good. Right? You guys are gonna do the same thing here. So what do we do react with that? Yeah, perfect. Great. All right, you want to have 2 pairs here. Oh, see over here. Super tiny here. Perfect, good. All right, so you ready? It should not start with H. What do you describe it? Oh, yeah. It's ugly like that. So like this. So this is the right. Yeah, you absolutely have the right idea here. This is not really that doesn't start with the room. It should start with the right. Showing the no. How is it going? All right. So do your best to make the arrows start at a lot, which might be too rough. But go to these arrows. Starting at, should be starting in the middle of this. So I know that you have the idea of exactly what's happening, but just to make sure we can show where they start. And when you see this is perfect. But when you draw on super small. Is this right? All right, you squeeze some really tiny arrows on there, squeeze a tiny bond. Good, this looks perfect. Good job. Okay, this was not a bond. This was me saying that NBS equals Br2. That's not a double bond. Stop that. You should start with a radical. Radical. You didn't draw. It's okay. You need to draw your CH because your CH is what's going to be the electron. Correct. You can ignore that. This is what we're starting with right now. All right, so you guys are doing great on this. The idea is, first off, we need to react with one of our H's. You guys know there's lots of H's in this thing, right? All right. And when we draw all of the H's, it just ends up being more confusing. Where is a radical going to be most stable? The tertiary one, right? So that's the one where we need to draw a hydrogen. So I'm going to draw a comically big CH bond right there to help us out. All right, so Laura, this radical, right, is gonna share its electron. And who's gonna meet it in between? Yeah, so one of the electrons from that CH bond. And we're missing something. What are we missing? Yeah, so that carbon's gonna get an electron. We started off with 2 electrons in our CH bond. We described where one of them went. So we need to tell me where the other one went. So where'd the other one go? You just said it. Yeah, to the carbon. So your other one, and you can draw these right next to each other, or you can do it on the other side if you want to. But it's really important to draw that both of these arrows start on the bond. And this arrow starts at the radical. If you're describing the movement of electrons, that's your one electron, and that's your pair. All right, so at that point, we would get boop, bop, bop, bop. All right, and you would get a BR2, because, well, we would get HBr. And this is where that nifty thing happens, where HBr then reacts with NBS to make a BR2, but ta-da, now you have a BR2. Right, now we're gonna do basically the exact same thing. Here's our radical. Our radical is gonna get together with one of the electrons in the BR2. The other one goes over to bromine, and we would just get pop, 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 pop. Oops, that was a lie, sorry. That should be really repetitive because it's just what we did. We got it? Okay. And so we could have done this reaction just fine with bromine radical and Br2. It would have been a lot easier because bromine's pretty cheap and easy to work with. Chlorine's a gas, so not quite as easy to work with. But let me show you when NBS really matters. Sorry, say that again. So yeah, if you see NBS, just treat it like Br2. You know how like extended release medication or pills are ones that just will slowly dissolve over time? Instead of you getting like a big bolus of some medication all at once, you'll just get little bits over a course of a long period of time. That's basically what NBS does. It makes it so you don't have to have just a bunch of Br2 at once. It just gives you a little bit of Br2 over time, which normally doesn't matter, but it would matter for something like this. So here we have an alkene. So if I added a bromine radical and Br2, you're going to have 2 different reactions that can happen at the same time to give you completely different products. One of them is that bromine radical can just go ahead and do just what we've been doing today. The other one is an old reaction that you may or may not remember from last semester, which is that Br2 can react with an alkene and give you bromines on both of those and break the double bond. And then there's also a third one where the bromine radical could react with the alkene, but it usually doesn't. So these radicals will normally react with sp3 carbons. So these are going to be the 3 that are most likely to react. But if you add Br2, you'll also get a side reaction. So we wouldn't use Br2, we would use NBS instead. All right, because if we start off with a double bond, Br2 is going to create problems. So we use NBS, slowly releases bromine, and then it goes on and does your radical reaction. And it only releases the bromine when you have a radical. The radical is going to be way more reactive than the alkene. So it saves your alkenes. Okay, so looking at this molecule right here, Casey, where do you think it would be most stable to have a radical? A, B, or C? Why? Okay, B also has 2 carbon neighbors. You were correct. So anytime you have a charge or a radical next to a double bond, what can you do? Resonance, exactly. And resonance makes positive charge more stable, a negative charge more stable, and it also makes a radical more stable. So yeah, so this would be where you would do it. You would do it at A, because it gives you the most stable radical. And it wouldn't work if you just started off with NBS. So what's going to happen here is we should draw out our hydrogen, that carbon. Your bromine radical is going to do its thing. Boop, boop. Those guys get together and make a new bond. Simultaneously, our third arrow would show this other electron of the bond going over to A. Right? All right. The product of that would have the same 5 carbons, and the radical at A. One thing you will never, ever, ever do is break up a carbon-carbon bond. So it's always going to be a CH that gets ripped apart. And the sp3 CHs are far more likely to end up with a radical than a double bond. Yeah, because Br2, there's a separate reaction. I'm going to draw it in red because it's basically not what we want. So an alkene reacts with Br2 to give you this. This was one of our reactions from last semester. You would end up with that, and then there'd be no more double bond. And then this molecule doesn't particularly react very well with free radical halogenation because all the electrons are being pulled to the brains. And so it kind of sends you in a different direction that you want. So if you wanted to make this, you just add Br2 without a radical. If you want to do this, you add bromine radical. But part of the reaction we're talking about today is you need a radical and some Br2. And the way to avoid adding both of those at the same time, which would give us both reactions at the same time, which is generally not what we want. We just want to steer it this way. So instead of Br2, you add this N-bromo-6-cinnamide, which through a long story that I put in the video, and I'm not going to worry about today because I'm not going to quiz you on any of it. But it ends up reacting with HBr that gets made halfway through the reaction right here. And then it will make a Br2 only at that moment. So only when we have the radical, we make a Br2. And so when we have the radical, your double bond is not likely to react with anything because the radical is the thing screaming for a reaction. So that's what will happen in the second step. So it's basically just to avoid having a whole bunch of Br2 hanging around, which has the possibility of this reaction. Yeah, so it's only when we have an alkene that we need to use NBS instead to avoid this competing reaction, which we don't want. All right. So Angel, tell me what happens now.
We halfway with the electron forming bromine bond. And then the other electron's going to go back to the other.
Perfect. Exactly right. And then we will have a new bromine here. So keep in mind, the general purpose of this reaction is that you start with an alkane, or in this case, an alkene, and you end up with an alkyl halide. You're substituting a hydrogen for a halogen. That's what all of these reactions have been doing, substituting a hydrogen for a halogen. So this would be the most stable, but practically, if you did this reaction, you would probably get 3 different products. You would get the bromine on A, mostly, and you get some with the bromine on B, somewhat, and some with the bromine on C, not as likely, but you'll have all of them. They'll all be mixed together, and separating them is a nightmare. So that's why this reaction is not great. It seems like a dream. If you look at your functional group interconversion flowchart, alkanes have been a dead end for us all year long. And this seems like a way out. But unfortunately, any reasonably sized molecule is going to have lots and lots of CHs. There's lots and lots of possible products. And with retrosynthesis, you guys are steering towards something that only gives you 1 product each time. Otherwise, if you get a 5% yield, it's the pits. And then you have to separate them all out. That's super hard to do. Nothing that you guys have learned in lab would let you separate these guys from each other. The 3 bromo from the 2 bromo from the 1 bromo. Their physical properties are almost exactly identical. So it's a super nightmare. So on paper, it looks great, but practically it's really not. But it's really important as one of the ways that we do polymer making. So, oh dear, it's not the button I wanted to push. Yeah, Josh Ring has joined the meeting. All right, so we're going to share a screen again, and we'll go back to that last one. All right. This was beyond what I showed you in the video. I was just trying to see if you guys could give it a shot. Everybody gave it a shot. I appreciate that. Some of them were right, some of them weren't. It's totally fine. So here's the deal. So you are a chlorine radical. We can put ourselves in the shoes of that chlorine radical. What do you want? You want an electron. All right. The most accessible electrons are the pi bond ones. So we've done reactions of pi bonds a whole lot in the past, and they always start with the pi bond electrons, which are loosely held, kind of floating around in those pi bonds, that the thing that's attracted to electrons is electrophiles. And really, a radical is an electrophile because it wants more electrons. So the electrons that it could take away are from a carbon-hydrogen bond, carbon-hydrogen bond, a carbon-hydrogen bond, a carbon-hydrogen bond, a carbon-hydrogen sigma bond, in which the electrons are held really tightly, and also a carbon-carbon pi bond, in which the electrons are pretty loosely held and really available. And so of all of those options, those pi bond electrons are going to be the ones that are easiest to swipe. So there's a little bit of a shift in how we look at this reaction, but overall it's the same kind of thing. That radical wants an electron. But the most accessible and easiest ones to grab are not from a CH single bond, they're from this carbon-carbon pi bond. So who didn't I call in? Alex, did I call on you today?
No, sir.
Well, would you do this for me? Tell me what you think.
That double bond is gonna give one electron for the and the other is just got
So
it goes back to the right.
correct. The two partners that were sharing those electrons were the carbons. And so that chlorine is going to make a new bond to whom? Yeah, so notice that in this case, you're not breaking any part of the molecule because you're breaking a pi bond. And when you do that, you still have a single bond left over. And so in our product, we will still have this. Because none of
It could be going like that.
it could. You wouldn't know which way it went, but this is symmetrical, so it wouldn't matter. So who's this chlorine attached to? Right, the way that we drew it, I guess it's attached to the carbon on the left. And what do we have on the carbon on the right? Perfect. So now that we've done this mechanism a bunch of times, does this make sense? So it's the same kind of mechanism, but talk to me about this molecule now. What have we made? Another radical, and what do radicals want? Right. So I don't need to add another radical, and I don't have Cl2 in here. If I had chosen to add Cl2, I could have put a chlorine on the other side. But if instead of adding Cl2, let's say I put in a drop of this, and I just had tons of ethylene, well, then the only thing hanging around would be more ethylene. Okay, well, just like in that first step, I've got a radical and I've got ethylene. All right, I'm trying to remember. I called on Yang, I called on Laura. Like, Chase, did I call on you today?
No, but go for it.
Great, Chase. What do you think is going to happen now?
For what comes out of that final.
Yeah, so we're basically going to do the exact same thing again. Do you see where we're going with this? So this can go over and over and over again, but this is absolutely, so if you will, put a line above this, because this is stuff for Monday. This is polymerization. And the difference is that here, what we're doing is we're ripping apart an alkene. Everything we did up until now was ripping apart a CH bond. But if you got an alkene in there, and no, we don't have Cl2, so you can't do that side reaction with Cl2. You just add a radical and an alkene. What we're doing here is that I've got chlorine. I'm going to bracket these things off. You got one little CH2, CH2. And then we've just attached another little CH2. But now that guy has a radical. And so it'll keep reacting with more alkenes and more alkenes. You'll just put CH2, CH2. And when will the madness stop? Yeah, maybe when you run out, or like that happy ending that I'm asking you not to admit is possible. Maybe two radicals bump into each other. But realistically, this just is going to make a long alkane chain. And that's what this is. That's what plastic is. That's what this is, and this is, and this is, and those things. And probably most of your shoes and a lot of your clothes is that what these are is just long chains of chunks of carbon. And so there are different ways to make polymers, which is why not all plastics are exactly the same. Some of them are flexible, some of them are very hard, some of them are stable in different conditions, some of them are easier to break down, all of that good stuff. But we'll look into plastics on Monday, but this is one of the main ways that we make plastics, is plastics are polymers. They are chunks of carbons just attached over and over and over and over and over again. And this is a thing that we do often, massive quantities, as opposed to this stuff, which I just got through telling you is not that practical and not that great. So this is something we're doing constantly. We are manufacturing massive amounts of plastics all over the world at all times using free radical reactions. So that's why free radical reactions are happening right now. Any questions? Nope, they're completely unrelated. We can use free radicals to make plastics. And if you have free radicals in you, you can make cancer, but free radicals just react with stuff. So they indiscriminately react with things. So free radicals in you start breaking apart stable, happy bonds indiscriminately, which if that happens in your DNA tends to go poorly. Because anything that messes with your DNA messes with replication and will often lead to problems like that. No, plastics are usually tied into the fact that they don't do very much. If you eat plastic, I mean, you're not going to digest it. So you're just going to eventually excrete it. They don't really do much, which is one of the great things about plastic and one of the terrible things about plastic. They don't tend to react, they tend to stick around forever. So thanks. We'll talk about all that stuff on Monday. Our last class will be a sad class about plastics. If you guys have any questions, technically we have 2 minutes left in class. Otherwise, have a lovely weekend.